The final configuration that we're going to consider is our common base amplifier. And so I have a simple example circuit shown here, and I want to point out a few things about this circuit. So first of all, we notice that our BJT orientation is a little bit differently. We have our base sort of towards the bottom and our emitter and collector on the top sides. So the reason is, of course, this is a common base, so our base is going to be connected to ground, and typically our ground is drawn on the bottom. And so we see that our base is connected to ground because we have this base bypass capacitor, C sub B. So therefore, our base is at signal ground. We notice that our input, in this case our small signal V of S, is connected indirectly to our emitter, and our output is defined as the voltage at our collector. So a couple other things to note is, of course, we have the circuit configuration is a little different than what we've seen for our common emitter and common collector. So we have these batteries, VEE and VCE, drawn explicitly, showing how we're biasing that BJT in the forward active mode. One other thing to point out that's a little bit different is that in this case we explicitly have included a load resistor, RL, which is connected to the output via this coupling capacitor, CC2. We did not have that when we considered the previous configurations for our common emitter and common collector. However, to be consistent with the book, I've included this load resistor here. We could have easily done the same thing and included a load resistor explicitly with our previous configurations to get a more comprehensive look at what those gains and input and output resistances are. So as we analyze this, we're gonna look at our small signal equivalent circuit and approach it from that angle, but we're not gonna go through all of the derivations. Rather, I'm gonna point you to where they are in the textbook, and we're just going to sort of state some of the key results. And then in the next video, we're gonna come back and we're gonna compare that to our key results from our common emitter and our common collector amplifiers. So we're gonna look at our small signal equivalent circuit, and we're gonna be looking at four things: our small signal voltage gain, our small signal current gain, our input resistance to the amplifier, and our output resistance of the amplifier. So again, we're going to start all of that by looking at our small signal equivalent circuit. And as always, what we can do is start by looking inside our transistor. So we have emitter, collector, and base in this case. So E, C, and B. And we're going to fill in what's in between those points, and then we're going to come back and fill in all the external components to the transistor after that. So between our emitter and the base, we know we have this resistor R pi. So we have some resistor R pi here, and now we have that it's going to be positive at the bottom because remember our V pi is at the base relative to the emitter. And our base current is going to be going from the base to the emitter because, again, we have an NPN. We can tell that because we have this arrow pointing outward from our BJT. Between our collector and the emitter, we have our dependent current source. So we can draw that like this. And so, again, that current direction is from the collector towards the emitter. So we get something like that, and this is GMV pi or beta IB. We have various ways we can define that. In this case, we're going to assume that our output resistance is equal to infinity, so our small signal output resistance. If we were not neglecting that, we would have it again between the collector and emitter, and it would be in parallel with that dependent current source. But to make things simpler, we're going to ignore that right now. All right, we don't have anything connected between our base and collector, so this is what it looks like for our transistor. So now let's relate this back to our circuit. And so first of all, we can see, as I mentioned earlier, this bypass capacitor means we neglect RB in our small signal equivalent circuit, and our base is just going to be at signal ground. From our collector terminal on the output side, again, we're going to deactivate any dependent sources. So here and here, these are going to become short circuits. So we're just going to replace that with a short circuit. And what we have on our output side then is we have our RC, which is going to be between the collector and signal ground. And our coupling capacitor is going to look like zero impedance. So we have our RL, which is also between the collector and ground. So coming down here, we can add those two things in. So we have from our collector to ground these two resistors, RC and RL. So let's just extend our ground over this way. And so this is RC, and this is RL. And so our V naught is defined as across those resistors. So this is V out. All right, so now on our input side, again, we're shorting this source. Our coupling capacitor looks like a short to AC. So we have RE, which is connected between our emitter and ground. And then we also have our RS in series with VS, which is connected between our emitter and ground. So we can add those two items in. So we have our input voltage, our RS value, and then we have our RE between the emitter and ground. So our small signal circuit with everything is going to look something like this. So this is RE, RS, and our small signal input voltage VS. Now, again, we're not going to go through the details of deriving the following equations, but sort of to write some key components here. So we're going to have an IE, or sorry, not IE, we're going to have an II. This is our input current. Our output current is going to be defined as the current in our load resistor RL. And I think that's going to be all we need to sort of understand these basic equations. So again, same sort of approach we would do in terms of analysis that we saw for our previous amplifiers. We're not going to go into it in detail. You can look on page 432 for this first piece at least, which would be our small signal voltage gain. So of course this is going to be defined as our output voltage over that small signal input, Vs. And so it turns out this is equal to Gm times the parallel combination of RC and RL divided by RS, and all of that is times the parallel combination of R pi divided by 1 plus beta in parallel with RE in parallel with RS. All right, so that would be our small signal voltage gain for this common base configuration. Like always, we can make some simplifying assumptions. So we know that our RS is a really small value, and as we said before, ideally it's going to be equal to 0. But let's just say it's really small. So if it's really small, it's going to dominate that parallel combination. So dominate that parallel combination. And so what that means is that this term right here is going to be approximately equal to RS. So then we have an RS canceling out with an RS there, and we're going to be left with just Gm times RC in parallel with RL. So we can say our voltage gain is going to be approximately Gm times RC in parallel with RL. And so what we see from this sort of approximation is that we do have some voltage gain that's going to be positive and greater than 1. So again, RC, typically on the order of k ohms. Our RL is going to depend on the application. If that's smaller, it's going to dominate. If it's much bigger, then the RC will dominate. And then our GM, typically tens of milliamps per volt. So the milliamps and the kV will cancel out. So we're still talking about a relatively large voltage gain. And again, note that it's positive as opposed to with our common emitter configuration where our voltage gain was negative. So if we now turn and look at our small signal current gain, so this is going to be on that same sort of area in the textbook, page 432 and also on 433 now, we can talk about our small signal current gain, which is of course our output current in that load resistor divided by our input current in that RS, our internal series resistance of the source. So that's going to be equal to Gm times RC divided by RC plus RL. So we see sort of that familiar current division ratio there. And then we're going to have the parallel combination of R pi over 1 plus beta, and that's in parallel with RE. Okay? And so again, we can make some simplifying assumptions. So let's say our load resistor is much less than RC. And so depending on our application, that might or might not be true. But for now, let's say it is. And also, let's say that our R pi divided by 1 plus beta is much less than RE. And so this is a little bit more comfortable assumption to make because again, our R pi is typically k ohms, but we're dividing by this beta plus 1, which, beta on the order of 100, is going to make that overall resistance here pretty small. If we make these two assumptions though, what we're saying is that this term is basically going to be our R pi divided by 1 plus beta, our RC over RC plus RL, and so that's an RL, means that this term is basically going to become 1. So then we're going to be left with our small signal current gain is approximately GM R pi divided by 1 plus beta. And we can recall that GM R pi is equal to beta. So we have beta divided by 1 plus beta. And so if you think back to our previous unit when we're introducing our transistor currents, we said that this beta over 1 plus beta is actually just alpha. So our gain for our common base circuit is just alpha. And so now our name for this alpha parameter should make more sense. So way back when we introduced it, we said this is called the common base current gain. And that'll make sense later on. And so now we've arrived at the point where it should make sense. Of course, this alpha is the gain for our common base circuit. So that's why we call it our common base current gain. All right, so 2 more items to look at, our input and our output resistance. So let's start with our input resistance. So our input resistance is going to be the resistance looking into the emitter. So looking into our emitter terminal. And so briefly, just coming back up here to this small signal circuit, we're saying that this resistance right here is going to be our input resistance. And oftentimes we'll see that this is just going to be referred to in the text as lowercase r sub e for this particular configuration. And so we're not going to go through the details of that, but if you look on page 433, you can see how this RIE is equal to R pi divided by 1 plus beta. And so again, that's often just called lowercase r sub e. All right. So typically this is going to be a small value again because the R pi is divided by 1 plus beta, where beta is typically large. So let's just say typically very small. And what that means is it's ideal for when we have currents as the input signal. So ideal for when currents are the input signal. And so of course we can think if it's seeing RIE or whatever source resistance we have, most of the current is going to go through the smaller resistance, which is our input resistance. And of course that's what we want. We don't want to be losing sort of information on that input signal to our biasing network. So the final thing we want to consider then is our output resistance for this configuration. And so our output resistance, let's first talk about it as looking into the collector. So coming back up to our small signal equivalent circuit, we're talking about now output resistance looking into our amplifier. So we're saying, let's talk about this ROC. And then as a later step, we're going to take a step back and say, what's our overall output resistance, including that load resistor, looking in from this point, and we'll call that R0, capital R0. All right. So again, same sort of approach we took with our emitter follower configuration or our common collector. We could do a test source, deactivate independent sources. The analysis related to this is on page 434. And what we see is that looking into the collector, our output resistance is R0 times 1 plus GM REQ plus REQ, where the REQ value is defined as RS in parallel with RE in parallel with R pi. But remember, our RS is ideally 0, so typically at least pretty small. So if that's the case, then that means that our REQ is also going to be about 0. So if our REQ is 0, then that means that this ROC is approximately just equal to the small signal output resistance of our transistor. So then our overall output resistance, looking in, including our load resistor and our biasing network, is going to be that ROC, which we said was just the R0, in parallel with RC in parallel with RL. And so all of these are going to be on the order of k ohms. So typically this, we would say, is then relatively large. And so because of that, it's going to be acting like an ideal current source. And so acting like an ideal current source in terms of loading effects. So ideal current source in terms of loading effects. So we want a large output resistance so that all of our output current is going to whatever load we have. And so again, for the loading effects, we talked about that on page 413 previously. So I know this is sort of a lot of information about all of these different types of amplifiers. So what we're going to do in the next video is we're going to come back and present a table that sort of summarizes and compares the pros and cons of using the different configurations.